Welcome back to Guide to Operating Systems 4th edition. This is Chapter 4. Today we're going to be talking about file systems. We're going to be listing the basic functions that are basically common to all file systems that you're going to see in operating systems. We're also going to explain the file systems used by Windows XP, Windows Server 2003, Vista, Server 2008, 7, and pretty much all the operating systems that we're going to come in contact with over the course of the rest of the semester. We're going to also discuss the file systems used by Unix and Linux as part of that process. And we're going to explain the Mac OS X Extended HFS Plus file system, including the new features added to Mac OS X version 10.6 Leopard. So let's go ahead and get started, shall we? Well, first and foremost, we need to talk about what is a file system. Well, all information is stored on a computer hard disk and has to be managed, stored, and retrieved through the file system. The file system allocates locations on a disk for storage and keeps a record of where specific information is kept. Some file systems also implement recovery procedures when a disk area is damaged or when the operating systems go down to prevent or to retrieve data that may have been corrupted. Uses a checksum process to do this. The overall purpose of a file system, however, is to simply create a structure for filing data. Now, in addition to that, file systems do other things. They help secure data and that kind of thing. But really, organizing data in a manner that you can easily retrieve it is the most important function of a file system. Think about your filing cabinet at home if you've got one, and what would happen if your 3-year-old got into it and messed it up when you weren't looking and you had to go back and try to retrieve something. You may find that to be an impossible task. So having the appropriate file system and managing it appropriately is very important. Now, when we talk about a file for the sake of this course, a file is simply a set of data that is grouped in some logical manner. It's assigned a name and it's stored on some sort of medium, usually a hard disk. Now, file systems that are used by operating systems today, they perform some basic general tasks. We will talk about some of those today. One of which is partitioning and formatting disks in order to store and retrieve information. Hard drives and pretty much all media devices have to be formatted in such a way that the file system can use them. And the file systems have a mechanism that they can use to partition and format those drives. They enable files to be organized through directories and folders. This is very important. You have to have a way of structuring the file system so that data can be retrieved. They also establish file naming conventions. How can files be named? How many characters can be in a file name or in a file path? These are some of the things that are sorted out when developing a file system. And they provide utilities to manage and maintain the file system and storage media in which they're on. Things like retrieving corrupted data, being able to defragment data that is stored on a drive. All those are done through a set of utilities. Typically, those utilities are universal to the file system. They provide for file and data integrity, another very important part. And it's basically a security function, making sure that your data, that the integrity of your data holds true after it's been stored. They enable error recovery or prevention. So they have tools generally that help fix the file system in the event of an error, or certainly to notify you and to allow you to take certain options. And lastly, but certainly not least, is the ability to secure the information in files. This is particularly true in today's IT environment where data theft and data corruption are ever present. Another term that you need to be familiar with, of course, is directory or folder. This is simply an organizational structure that contains files and may additionally contain other subdirectories, or we also call those subfolders. A directory or folder is just another unit that we use to help structure our data. Now, directories may store the following information within the actual properties of the directory. For instance, date and time of the directory was created, the date and time that the directory or file was last modified, the date and time when the directory or file was last accessed, the file size or directory size, the directory or file attributes such as any security information or if the directory or file was backed up recently, and if the information in a directory or file is compressed or encrypted, and in most Windows file systems it's either or. One of the things that we probably ought to talk about today is organizing your file structure. You'll be surprised when you get out into the IT world how the organization of the file structure for many people is taken for granted. A chaotic file structure, of course, makes it difficult to run or remove programs, and it makes it difficult to determine the most current version of a file or directory that you may have. It typically makes users spend more time looking for specific files, and during that time, of course, you're being non-productive. So having a organized file structure is very important in maintaining productivity, particularly in a corporate environment. Organizing a file structure for a home user, usually not that big of a deal, right? But when you start getting out into the corporate world, there are whole meetings devised to how we're going to organize a new set of files so that our users can be productive with those files and so that we can secure them properly, which is very important. One of the things that we'll talk about is at some point is how permissions are inherited in a file structure, and therefore how you organize files can assist you in securing data. Some users keep most of the files on the computer's primary level. We refer to that as the root directory or the root folder. This is generally a bad practice when you just start sticking things in the root folder and creating this very lateral file structure. So we recommend a limited number of file folders within the root directory for the very reason that it's easier to organize. Some programs will use an automated setup that will suggest folders for new programs. Typically in Windows, when you install a program, it's going to install by default under the Program Files folder. This is something that's set up when the vendor is creating the software. They are aware of the file structure for that particular Windows environment, and they will create an install package that is appropriate for that. Oftentimes it's a good idea to take advantage of the default file structure that's being presented to you. There are other times when you may choose to alter that file structure if it's going to improve functionality, performance, or if you are organizing your data in another way. Basically, to avoid chaos, design the file and folder structure from the very start. Think about how you're going to organize the data before you start accumulating the data so that you will have a consistent and organized file structure from start to finish. This is particularly true on server infrastructures where multiple users will be dependent upon that file structure so that they can be productive. When designing a file directory structure, let's consider some of these general practices. As I said before, the root folders should not be cluttered with files or too many directories or folders in that directory. Each software application, of course, should have its own folder or subfolder, and it's particularly true if you have multiple versions of the same software application that are going to be running in unison. Microsoft Office allows for that, where you can run two different versions of Office installed on the same computer. But it's important to make sure that you keep those versions separate so that when it comes time to get rid of one of them, you don't have to really sort through the hundreds of files and folders that are indicative of each particular version. Similar information, similar data should be grouped in some manner. Accounting systems should be grouped, or Office productivity software could be grouped in a folder. But grouping similar data structures helps with productivity. Operating system files, of course, should be kept separate and they should be kept protected from the general user public. And directories and folders should have names that clearly reflect the purposes of that particular data. A folder named shared would contain, of course, all the documents that could be shared by many users. And then in theory, those documents would be subcategorized in some manner. And that's a good thing. Here's an example of a directory structure. As you can see, we have a limited number of folders that are off the root. This is a typical Windows directory structure. We have Windows, program files, inetpub, forms. We have all kinds of forms subcategorized in the forms folder. Users, same thing. The users folder is generally the home folder, right, folks? This is the folder that each user is assigned individually and customized, and that is also the users folder in Windows 7 anyway is now structured off the root as it was in XP, except we call that documents and settings. And then of course a shared folder could also be off the root as well. Hard drives are the general method in which we store data over a long term. Hard disks arrive typically from the manufacturer with what we call low-level formatting already in place. A low-level format is a software process that really marks the location of the tracks and sectors for that hard drive, and we'll show you tracks and sectors in a minute. A track, for all intents and purposes, is like several circles around a disk, and each track is divided into sections of equal size, which we call sectors. Think about a record, and if the record is spinning around, and if each time it spin around it was a solid circle, we would call that a track. And the data that it was reading inside that circle would have been equally distant, and we would call that a sector. This is an example of how a track and sector is designed on a hard drive. The tracks, of course, are circular, and sectors are equidistant within a track. Now, you have to remember that a hard drive is not one platter, it's multiple platters. We call those cylinders. Cylinders are tracks that line up on each platter from top to bottom. So think about having, if you take a bunch of CDs and you put them in a stack, that's kind of the way your hard drive looks, except they're magnetic, typically metal disks. And if you look at a sector and you look down on those CDs and all those sectors lined up, we would call that a cylinder. Block allocation is the process of dividing the disk into logical blocks. We call those clusters, which correlate to sectors, heads, and tracks on a disk. This helps keep track of where specific files are stored on the disk. And depending on the operating system file system that we're using, we can actually adjust the size of those clusters. And this is important for several reasons, and we'll talk about those in a little bit. Data regarding block allocation is stored using one of typically two techniques in today's operating system file structures. File allocation tables, we see this particularly in older file systems, we call that FAT. One of the more common file systems still in use today is FAT32. New Technology File System, or NTFS, which is now the industry standard particularly for Windows environments, and of course Unix and Linux file systems. They use various locations on the disk, depending on the operating system, to store a special type of file that is used for directory and file allocation information. Don't worry about it, we're going to elaborate on it in just a few minutes. Partitioning. Now, as I said before, file systems come with a utility that allows them to partition a hard drive. We have to partition drives. It is one of the most rudimentary ways that we structure hard drives so that data can be stored on it. But partitioning is the process of blocking a group of tracks and sectors to be used by a particular file system, such as FAT or NTFS. Now that means that with multiple partitions, I can have multiple file systems. After partitioning, the disk must be high-level formatted in order for the operating system to store files. We generally do that through the format utility. Now, it might be necessary for a disk to have more than one file system. As I said before, we can do that. We will require a partition for each of the file systems. So for example, if I want to run Linux and Windows 7 on the same computer, I would have two file systems. Now, we get around that now with virtual machines, but if you're going to be building this on a designated device, two partitions will be necessary. Now, another term that we use often is logical drives. Logical drives we see a lot of in today's file system environments. This allows us to create multiple logical volumes on a single disk and assigning drive letters to each volume. It's important to note that a logical drive does not have any physical differentiation. It is simply a way of defining a partition so that the operating system itself will acknowledge that it is a separate method or a separate entity within the partitions. Alright, now when a partition is created, information about that partition is going to be stored in a special area of the disk. We call that the partition table. In Microsoft DOS, Mac OS, and Windows, we call it a disk label when we're using Unix and Linux. But essentially, it's the same thing. It is simply a data set that allows us to store information about how that partition was created and organized. Another piece of the disk that is reserved is going to be known as the boot block in Unix and Linux and in Mac, or we call this the master boot record in DOS and Windows. The master boot record will consist of four elements. The boot program, which examines the partition table to determine which partition to boot from. The disk signature, which stores information about the disk and is used by management software such as Windows registries. The partition table, which pretty much differentiates the active partition from other partitions. And the end of the MBR marker, which is where the master boot record ends on the disk itself. Now, not all operating systems will support partitions the same way. This is very important. Each operating system will use its own specific utilities to create partitions. Now, when we talk about formatting, we're talking about that higher level formatting that needs to be done in order to organize clusters onto the partition itself. Formatting is the process of placing the file system on the partition. It is necessary in order for us to order and install an operating system. And after the operating system is installed, we typically have disk management tools that can be used to partition and format additional free space for us to store other data. We can also use the format command from the command prompt window. This allows us to not have to be constrained by the GUI. We can use several types of switches, which are extra codes in the programming that we use when we're actually typing out commands, to explain to the operating system exactly what we want the format command to do. And we can also use this to view a list of these switches by simply typing in DOS or in the command prompt format /?. So what happens when we store a file to the disk? Well, data is written to clusters on the disk. The file name is stored in the folder along with the number of the first cluster the data is stored on. When the operating system fills the first cluster, data is written to the next free cluster, and the fat entry corresponding with the first cluster points to the number to the second cluster used. When the second cluster is full, the operating system continues with the next free cluster, and the fat entry for the second cluster will point to the number of the third cluster used, and so on. Why? Because data is not necessarily stored sequentially. We'll talk about that later. We will call that fragmentation of data. Now, when a file is completely written to the disk, the fat entry for the final cluster is filled with all ones. In the fat file table, that means that is the end of the file, and we usually refer to this method that we're discussing as the linked list method. Clusters, as we were talking about before, are a fixed length. When a file does not use all of the space in a cluster, the rest of the cluster is unusable. This is where it is important in some instances to have that ability to create smaller clusters on a file system. Unusable spots are marked in the FAT as bad clusters, which are never used for file storage. Now, each partition stores an extra copy of the file allocation table, FAT table, in case the first copy gets damaged. There is only one copy of the root directory on each partition, and the FAT table and the root directory are at the beginning of each partition and always in the same location for consistency's sake. This is an example of how in a FAT directory structure we would see a typical volume. We would have the partition boot record, the main FAT table, the backup FAT table, and then the root directory, which has room for 512 entries in FAT16, but it's unlimited for FAT32, and then the remaining area would be the data area, and of course the size would vary depending on the size of the disk. Each FAT allocation table directory contains file name, file change date and time, the file size, and any file attributes for that particular file. An attribute can indicate whether a file is set to read-only, archive, which means that the next time you run the backup utility, it will back up that file, system, which indicates that it's a system file necessary for the operating system, or if the file, for whatever reason, is hidden. You can have more than one attribute for a particular file or folder. Now, in Windows file systems, we have several file systems that we can support. Windows XP, Vista 7 2003, and Server 2008 will support 3 file systems. Extended FAT16, you don't see a lot of that anymore, FAT32, and of course today's big standard NTFS, which by the way is the default file system for Vista and 7. Now, these operating systems also support file systems for DVD, CD-ROM drives, and USB devices, which we call flash drives. Extended FAT16 evolved from FAT16, which we used in earlier versions of Microsoft DOS and Windows. This goes all the way back to Windows 3.1, 3.0, Windows 95, 98, and even Millennium Edition used FAT16 or extended FAT16. Now, in an extended FAT16, the maximum size of a volume is 4 gigabytes. The maximum size of a file was 2 gigabytes, and it has been around for a long time. It's a file system that is not only read by Windows, but other non-Windows operating systems like Unix and Linux, and it's considered one of the more stable file systems. Now, in extended FAT16, we did have the ability, or started the ability, of running long file names in Windows operating systems, which allowed us to contain 255 characters in a file path, and it's not case sensitive. Well, FAT32 started, or support for FAT32 started with Windows 95 Release 2. It was designed to accommodate these larger capacity disks that started coming out at about the same time. And FAT32 provides a root folder that does not have to be at the beginning of the volume. It can use disk space more efficiently than FAT16 because of the cluster sizes. It uses a smaller cluster size by default, which means that when it reaches the end of a file, you don't have to write so many ones, and therefore over a period of, as you span the volume, you end up with more space. Now, the largest volume that you can have in FAT32 that could be formatted was 32 gigabytes, and the maximum file size was 4 gigabytes. FAT32 offered a faster response on 1 or 2 gigabyte partitions, but when you got into the bigger partitions, it tended to slow down. Now, FAT64, we don't normally think about FAT64. We usually call it exFAT. You see exFAT on things like flash drives and removable media. Why? Because exFAT is very good at storing very large files. It's a proprietary file system that Microsoft created for mobile personal storage. It's not very secure. It has the same security features as FAT32, essentially, unlike NTFS, which has extremely good security measures. So if you're going to be storing large amounts of unsecured data, exFAT may be something to think about. It is a good choice for USB flash drives that may store large files like pictures and videos and stuff. Once again, provided you don't have to secure the flash drive, and it's available in Service Pack 1 for Windows Vista, Windows 7, and all Server 2008, as well as Mac OS X Snow Leopard. And support is available for Linux from a third-party utility. NTFS, as I said before, it's now the industry standard. NTFS is the dominant Windows file system for all Windows operating systems that goes all the way back to Windows 2000. It uses a master file table, or MFT, instead of FAT tables. Now, the master file table and the related files take up about a megabyte of the disk space, not a whole lot. When a file is created, a record for that file is added to the MFT. It will contain additional attributes, including all the security settings, ownership, and permissions that we think about with NTFS. This is very granular in comparison to FAT32 and earlier file systems, and that's one of the reasons why it is the industry standard today. I can micromanage this file or this directory or all the subdirectories through NTFS as far as security permissions and access permissions. The MFT file record reflects the sequence of clusters that a file uses. It is possible to have multiple file names that will refer to the same file. We call this hard linking. For anyone who's familiar with Unix and Linux, this is something that you are probably already familiar with. Windows Vista, Server 2008, and Windows 7 use NTFS file version 6. It is generally the default file system. You can, in some instances, revert back to FAT32 when it asks you what you want to use, but by default, NTFS is the choice for the file system. Windows XP and Server 2003 use NTFS version 5, an earlier version of NTFS, while Windows NT 4.0, which originated this whole NTFS file system to begin with, uses the original release NTFS 4. Each one of these releases, 4, 5, and 6, have brought about new utilities and new methods of securing data. So each version is more and more granular. Basic features of NTFS, regardless of the which one you're using. Well, you can use long file names. That 255 character file name still works. One of the things you need to think about with 255 character file names, particularly in Windows environments, is that also includes the file path. So whereas we talk about you don't want a very lateral file system, you also don't want one that goes too deep, because if you get over that 255 character file path, weird things will start happening to your data. So remember, you want your file paths to be no more than 255 characters, including the file name and all the directories above it. NTFS has several built-in security features. It has better file compression than FAT. It has the ability to use larger disks and files than FAT, and file activity tracking for better recovery and stability than FAT. It's an all-around better file system than FAT or FAT32. It also has portable operating system interface for Unix available. We call that POSIX, POSIX support. It has volume striping and volume extensions. Volume striping, it allows us to span a volume over multiple disks, and that will allow us to increase performance. Doesn't do a whole lot for security or redundancy, but it does allow us to improve performance. And it also has, in general, NTFS has less disk fragmentation than FAT. NTFS is equipped with security features, as I said before, that meet U.S. government C2 security specifications. This goes all the way back to Windows NT, which was the first Windows file system to meet these rigid specifications. This refers to high-level, top-secret standards for data protection, system auditing, and system access. Some examples. System files can now be protected with NTFS so that only the server administrator has access. Folder and databases can now be protected with read access but no access to change data. And the public folder can give users in designated groups access to read and update files, but they're not allowed to delete them. This is just some examples of the granularity that you can have with NTFS. Some files in NTFS can be compressed upwards of 40%, which saves a lot of disk space. NTFS has the ability to keep a log or journal of file system activity. We refer to that as journaling. We'll talk a lot about that in subsequent semesters. And it makes it possible for files to be restored in the event of a power failure. Very important. NTFS, as I said before, supports volume striping. This is the process of equally dividing the contents of each file across 2 or more volumes to extend disk life, enable fault tolerance, and balance disk load for better performance. NTFS has hotfix capabilities as well. If a bad disk area is detected, it's going to automatically try to copy that information to another disk area that's not damaged and rebuild it. Now, in addition to the NTFS 4 features, NTFS 5 added some additional features. With NTFS 5, we had the ability to encrypt files. Now, bear in mind, you cannot encrypt a compressed file and vice versa. So, you can either encrypt or compress, but not both. No system reboot is required now when NTFS 5 came on the scene after creating an extended volume. In older file systems, that was mandatory. And the ability to reduce drive designations is also included in NTFS 5. NTFS 5 is also the first time we saw indexing, which allowed us for faster access or faster searches of file systems. And the ability to retain shortcuts in other file information when files and folders are placed in other volumes. We take that for granted now, but that really came on the scene with NTFS 5. The ability to establish disk quotas was also something new to NTFS 5. This allows administrators to control how much disk space users can occupy. This is on a per volume level, not on a per folder level, folks. So if you have a volume, you can have several volumes and just several disk quotas, one for each volume for a particular user. NTFS 6 had some other new features as well. This is when we started talking about transactional NTFS, which is used to perform operations in transactions, which is all at once or none at all. Partition resizing. This allows administrators to expand or shrink partitions on the fly. This is a very nice feature when particularly in corporate environments where you need to add additional space. Self-healing. The check disk utility runs in the background now with NTFS 6. To correct hard disk problems, instead of having to take the volume down and run the utility manually, you can, with NTFS 6, it's done automatically for you. The check disk utility, since we're on the topic, can detect and fix an extensive set of file system problems in FAT and NTFS file systems. This utility is available in all versions of Windows, starting with Windows 2000. The most common problems found are files with 0 sizes, which is caused when the file is not properly closed or when chains of clusters contain no directory entries. Now, Windows 2000 and later versions have built-in disk defragmenting tools. You don't have to have a third-party utility like we did when we were running earlier versions of Windows. Disk defragmentation tools allow us to rearrange data on the disk in a continuous fashion, ridding the disk of scattered open clusters. So think about a disk when you buy it, it's brand new, and you start adding data to it. It's going to be added generally in a sequential fashion. But at some point you start erasing data, moving data, and when you do that, you start creating open clusters. Now, the operating system, the file system, is going to try to store data in those open clusters as needed. But what ends up happening is, since those clusters are no longer sequential, It's entirely possible for data to start getting fragmented. Now, fragmented data decreases the performance of the hard drive. It increases wear on the hard drive, etc., etc. So running the disk defragmentation tool on a routine basis is important for general file system maintenance. This is just a table. Should be in your book, that compares FAT16, FAT32, FAT64 or exFAT, and NTFS. Some of the more important things were things like the total volume size, the maximum file size. FAT16 and FAT32, of course, were compatible with floppy disks. FAT64 and NTFS are not. You have limited security features all the way up to FAT32. And exFAT, but NTFS has an extensive security and auditing operations available for you. File compression, you don't see file compression supported as part of the file system until you get to NTFS. We usually did file compression in previous versions through some sort of utility that was an extra utility or third-party utility. File activity tracking is only available in NTFS, as well as POSIX support. And of course, if you go down to table 4.4 continued hotfixes, we see hotfixes in exFAT and NTFS. Large database support is available from FAT32 onward, and multiple disk drives in one volume. The only Windows file system that allows that is NTFS. So let's talk a minute about, since we've talked about Windows for so long, let's talk about CDFS and UDF. Windows versions after 2000 recognized some additional file systems used by peripheral storage technologies. CD-ROM file systems, that is what we refer to as CDFS. Yes, CD-ROM file systems are different. They are supported so that operating systems can read and write files to DVDs and CD-ROM drives. UDF, or Universal Disk Format, is also used on DVDs and CD-ROMs. We usually use this for huge file storage to accommodate movies and games. Most people are probably familiar in some way or have heard of UDF. The Unix file system, well, there's some differences in the Unix file system than there is in the Windows default file systems. There are many different file systems that can be used with Unix, for starters. Unix, in many ways, is a very versatile operating system. The file systems that are more native to specific Unix operating systems than others. Some versions of Unix and Linux support the Unix file system, or UFS, which is the original native Unix file system. UFS is what was originally put on the first release of Unix. UFS is a hierarchical file system, not surprising. It is expandable, it does support large storage, it provides excellent security, and it is reliable. So, back in the old days, when you really wanted to have a secure, reliable file system, Unix was the answer. Many qualities of NTFS were modeled after UFS. Most people don't realize that. Things like journaling and hotfixes, for example. Now, in Linux, the native file system is called the extended file system, or EXT. In some cases, EXTFS. EXT is modeled after UFS. It's no surprise there, and it enables the use of full range of built-in Linux commands, file manipulation, and security features. The first EXT version had some bugs. EXT2 was considered a reliable file system that handles large disk storage. EXT3 had some journaling capabilities added to it, and EXT4 allowed for some extended file sizes all the way up to 16 terabytes. Both UFS and EXT use the same structure. It's built on the concept of informational nodes, or inodes. Each file has an inode, or basically a number, that's assigned to it. An inode contains general information about that file that will include the user and group ownership, permissions, size and type of file, the date the file was created, and the date the file was last modified and read. Each disk is divided into logical blocks. We have one called the superblock, which contains information about the layout of the blocks, sectors, and cylinder groups within the file system. The inode for a file contains a pointer or a number that tells the operating system where to find that file on the hard disk based on those logical blocks. Inode 0 will always contain the root of the folder structure and is the jumping off point for all other inodes. A Unix or Linux file system can have many file systems. We can mount file systems as a sub-file system within the root file system. Matter of fact, we can mount points in the file system in Unix anywhere. All file systems are referred to by a path. The path starts out with a /. Now the / indicates the main root directory of the file system. Directories in the file system contain a series of file names. Unix or Linux allows the use of long file names like Windows, which may include any character that can be represented by an ASCII code. This is an example of the Unix file system, and you can see where we have mounted a different file system here, and we've also created a symbolic link. A symbolic link allows us to use the same file but refer to it in different locations in the file system. The Unix file system disks are referenced by a special inode which we call a device. And there are two types of devices: a raw device, which has no logical division in blocks, or a block device, which of course does have a logical division in blocks. Now, devices are normally kept in the /dev folder, which stands for devices. The symbolic link, as I said before, is used to link a directory entry to a file that's on a different partition. It's simply a pointer. The Unix file system doesn't surprise you by now. You must first partition a disk to use the Unix Linux file system, just like Windows. The command to partition the disk is going to differ slightly. Most Unix systems either use an fdisk or a format command. Typing man fdisk or man format, man being the manual pages to give you, it's kind of like help pages in Unix or Linux. Typing man and fdisk or format at the command prompt will give you an overview of the available commands for each of those commands that you may use to format the file system. Now, in Unix, once the partition is made, a file system can be created. This process, as I said before, very similar to Windows. You must know the device name of the partition on which you wish to create the file system. You can type new fs followed by the name of the device. The new fs command is not available in all versions of Linux, however. You may have to use something called the make fs command instead. Now, when a file is saved to a disk, the system first stores part of the data to memory until it has time to write to the disk. Now, some things you need to be aware of in the Unix file system. When a file is saved to the disk, the system first stores part of the data to memory until it has time to write to the disk. Now, this create some caveats. For instance, if a computer is shut down prior to the data being written to the disk, you can end up with a damaged file system. Now, Unix and Linux systems should always be shut down using proper shutdown commands. You can manually force a write of all the data in memory by using the sync command. If you need to shut down the system unexpectedly, you can use the sync command and then shut the system down. Another utility in Unix file system is the FS check, file system check. It verifies the integrity of the superblock, the inodes in all the cluster groups, and all the directory entries. This is very similar to fdisk or check disk in Windows. The Unix file system, this is a chart of some available commands that you should be aware of. In particular, copy, fdisk, which is formats the partitions of the disk in some of the Unix systems such as Linux. The format command, which formats the partitions in a disk in some Unix systems, including Solaris. the list command, ls, which lists the contents of a directory. The make directory command, which creates a directory. You have the make file system command, which creates a file system, but you have to add parameters. mv, moves a file to a different directory. rm allows you to remove the file or directory altogether. Sync, as I said before, forces information in memory to be written to the disk. Touch is just a way of creating an empty file, and umount, which is a way of unmounting a file system. The Macintosh file system, in some ways, is very similar to the Linux file system. The original Macintosh file system, or MFS, was created in 1984. It was limited. It allowed for keeping track of 128 documents, applications, or folders. That was reasonable back then. Typical storage device was 400 kilobytes, basically the size of a floppy drive. In 1986, Apple created the hierarchical file system, or HFS. This allowed us to divide a volume or disk partition into allocation blocks, similar to clusters on a PC. In 1998, Apple released the Mac OS 8.1. It had a new file system, which we call Hierarchical File System Extended Format, or HFS Plus. In Mac OS 10 version 3.0, the Mac Operating System Extended HFS Plus includes new features. It allows for a case-sensitive format to make the file system more compatible with Unix and Linux systems. That's right, in Unix and Linux, files and folders are case-sensitive, unlike Windows, something to be aware of. This is also the first time we start seeing journaling available for Mac OS. And the ability to store up to 16 terabytes of data is also available in this file system as well. The first two sectors of a Mac formatted disk are the boot sectors or boot blocks, and then we have the volume information block. Now, the volume information block contains catalog B tree, which is a list of all the files on the volume and keeps track of all the files through name, location, and the folder structure, as well as its physical location. Macintoshes can read and write to disks from other operating systems. Mac operating system has always supported what might be called medium file names, which are up to 31 characters. Short file names are generally 8 characters or less, which was indicative of the first versions of DOS and Windows 3. Any character may be used in a file name except for a colon. That's because the Macintosh paths are written as separated entities, such as what you see here on the screen: hard drive : system folder : preferences : finder prefs. That's a file path in Macintosh. Mac uses type codes and creator codes instead of file name extensions as Windows does. That means that files created with Apple's Simple Text Editor have a type code of APPL and a creator code of ttext. Macintosh files can contain two parts or forks: a data fork that contains frequently changing information, such as word processor data, or a resource fork, which contains information that is fixed, such as the program icons, menu resources, and even splash screens. Now, because Mac files have type and creator codes and two forks, can create problems when storing files on non-Macintosh servers. The Mac binary is generally a format which joins the forks into one and safely stores the type and creator codes as finder flags. Apple's equivalent to the Windows shortcut is what we call an alias. Now, that was introduced back in System 7 back in 1991. The system level alias manager is what keeps track of the original aliases, and the word alias is the extension that we tack onto a file name when an alias is created. That is italicized as well. So Mac OS 10 comes with two disk utilities that we need to talk about: the disk utility, which manages the disk drives, and then something called disk first aid. Disk first aid allows us to repair disk problems very similar to check disk in Windows. Mac operating system 10 also comes with a utility which we refer to as Sherlock. Its job is to search disks for file names and text within files. We don't use Sherlock anymore. Now we have something called Spotlight. Spotlight replaced Sherlock in Mac OS 10 10.4 Tiger Edition. So if Sherlock doesn't work well, then you know that it's going to be Spotlight for all the newer versions of Mac OS. And you see that Spotlight is there to search for particular files. This is a typical search for the Mac OS 10 Snow Leopard, and it will show that your results are broken down into categories such as web pages, system preferences, definitions, etc. The Macintosh file system, like I said, when a Mac is not shut down properly, very similar to Unix, a disk integrity check will automatically run at the next startup just to ensure that no corruption occurred. Macs will boot from a DVD or CD-ROM or various SCSI devices. To boot from a DVD or CD-ROM, you simply press the C key while it's booting up, and that will tell the operating system to look for a DVD or CD-ROM device. Pressing the Shift Option Delete Apple or Soda key while booting will bypass the internal hard drive altogether and will boot from the next drive in the SCSI chain. Let's summarize. This is a long chapter, so let's go ahead and take this opportunity to summarize. For the user, files are the bread and butter of the operating system. This is what we use computers for, to store data, compute data, and computing data without a way to retain it is futile. So having a reliable, efficient way to retain data is very important. So besides containing the operating system kernel, files hold documents and programs, data as we refer to it, on which users rely upon. Files are made possible by a file system that enables them to be created, written, managed, and stored on disk media. There are all kinds of disk media out there. We've talked about a few today. We've talked about hard drives, flash drives. We've talked about DVD, CD-ROMs. That's just scratching the surface. There are other types of media out there that we can store data on, and that changes on a daily basis. All operating systems must have file systems on them in order for them to work. They have to provide a naming convention, a way for to store the data. They have to have a way to partition and format those disks so that data can be stored upon them. Besides creating and modifying files, file systems should also offer the ability to defragment and optimize your storage devices. That includes defragmentation, compressing file contents, ensuring data integrity, a way to secure files, and a way to control removable storage media in today's environments. The main file systems that we use in Windows pretty much since 2000 is extended FAT16, FAT32, and NTFS, with NTFS being the predominant file system and nowadays the default file system for these operating systems. In FAT16 and FAT32, the file system creates something we call the File Allocation Table, or FAT table, to store information about files. FAT32 is more robust, of course, than FAT16. Makes sense. It was an upgrade. It provides for the use of more clusters and larger partitions. exFAT, however, allows us to store on mobile storage devices very large files. It's a very reliable system for storing large amounts of data, provided you do not have to store the data securely. If you have to combine security with an excellent file system, then NTFS is your choice. It is the native file system from 2000 on up in Windows environments. It does offer better security, larger disk and file sizes, better management tools, and greater stability than pretty much any of the other file systems previous to NTFS. An important command that you need to be aware of, check disk. It's an important disk verification and repair utility that works in all of these file systems in Windows. Unix and Linux support, well, they may support many different file systems, but typically you're going to see UFS or EXT in these environments. UFS and EXT use information nodes or inodes to organize information about files. Different varieties of Unix and Linux use different file system utilities, such as fdisk and format, to partition and format disks. The fscheck or file system checker utility is used to verify the integrity of Unix and Linux file systems, very similar to disk check in Windows. Mac OS X uses the Mac OS Extended or HFS Plus file system. This is an enhancement of the original HFS system, introduced in 1998 with Mac OS 8.1. Two important Mac OS X disk tools would include the disk utility and disk first aid. Table 4.8 shows the disk management utilities you have learned about in this chapter. Of these tools, the Mac OS X tool might be the most one-stop because you can use it to configure, repair, and manage the disks all in one tool. That's it for this chapter. They've literally just scratched the surface on file systems. There is so much information about file systems, and there are a lot of file systems out there. But these are the predominant file systems with our popular operating systems today. And as we progress through the remainder of the semester, we will elaborate a little bit more on file systems. But this is an excellent overview, and I've enjoyed discussing it with you. We'll talk again next week.